supermassive black holes and how they affect galaxy and galaxy clusters. There you go. All right, so I'll let you take it away, Mark.
Okay, well, thank you very much. So this is the first time I've ever given this talk, and it's about a paper that's still in preparation. But rather unexpectedly, my research journey has intersected with work done by people right here, some people in this very room. Because I found I had to take a closer look at the relationship between black hole mass and the mass of a halo around it. And what brought me on this path was I'm interested in how black holes interact with the gas around them on large scales. So that's the picture on the left. This picture in the middle is a recent picture from, and I'll show it bigger on one of my slides. It's from the illustrious TNG simulation, showing that on scales of halo mass of 10 to the 13 solar masses or so, their feedback algorithm suppresses the baryon fraction out to pretty large radii. And in fact, we're not accustomed to visualizing things like this, but the blue areas are where the local baryon density is below the cosmic mean, and the red ones are where it's above the cosmic mean. And the action of feedback is to actually suppress the baryon fraction where most of the matter is. And the complementary act is actually baryons, the low density parts of the universe are actually baryon rich compared to the cosmic mean. And that event has a great deal to do with the quenching of star formation. You'll see bigger diagrams like this. This is from illustrious TNG, where there's a halo mass here, and this is in total injected kinetic energy. And we've injected enough kinetic energy with the black hole, star formation gets shut off in the simulation. So these are the elements that will be swirling around. Interesting. Yeah. Does my slide advance? Yes, it does. All right. I've been giving, most of my talks have been colloquia in departments of physics and astronomy. So we have to acquaint people with the basic anatomy of a galaxy. I have this slide here. You probably know this already. So has a disk. Okay. There's the bulge, and there's a halo around it, and it's got a thing called the interstellar medium. And into the 90s, I started, so one of the things I've done with my career is I spent some time writing a textbook, an introductory astronomy textbook that has become widely used. That didn't have to work out that way, but it did. And in the 1990s, when you had a diagram showing the anatomy of the galaxy, that's pretty much the sum of it, except right near the end of the 90s, we came to appreciate that the central black hole is intimately related to the galaxy through work that has made Laura famous, right? Or maybe infamous. We'll get to that part. And so, so the black hole's mass is highly correlated with the bulge mass of the stars and the central velocity dispersion, indicating there's some sort of intimate relationship between the evolution of the black hole and the evolution of the galaxy that has fueled many research careers over the last 20 years. So thank you for that. The thing that's more of a 2010s edition is the idea of the circumgalactic medium. I think we all knew there was gas out there, but I think the Hubble Space Telescope in particular, through observations of quasars in the distance and the absorption that happens on lines of sight close to galaxies like the Milky Way, has shown us that most of the gas associated with the galaxy is circumgalactic. There's at least as much gas out there than there is in the form of stars in the galaxy. When you look at the abundances, you find maybe even as much of the elements made in that galaxy are outside the visible part of the galaxy as are in the stars of the galaxy. And that's gotten a lot of people very serious about understanding the baryon cycle that takes gas into a galaxy, makes some stars, some of it gets ejected, and some of it may even get recycled. So this is, since I'm speaking to astronomers and not physicists, you're probably already aware this is a big theme in today's research, endorsed by our decadal survey, once again, as an important thing. In very brief, what feedback does is fundamentally simple. Inside the galaxy, baryons are able to condense through radiative cooling and get denser and denser and denser. And as they do that, they release gravitational potential energy. And the most extreme form is if they start falling into a black hole. That's the maximum gravitational potential energy you could possibly release. But as that happens, some of that potential energy gets transferred. You have, in this case, you have jets shooting out. And we've known from morphology of radio galaxies for decades that they're running into something. Whatever that something is hard to see. But in the 70s, people said there has to be some sort of medium around the galaxy because the jet's slowing down, just morphologically. And when it slows down, it's dumping its energy into what's ever out there, and whatever is out there gets less bound. So really, it's a gravitational potential energy exchange. And you release it in the inner part, it ejects in the outer part. So that seems simple enough. The hard part is understanding how a black hole, they're bigger than this. I'll hold my fingers, very close together to indicate small, that they're big. Down at the central parsec of the galaxy is somehow aware of the environment at tens or hundreds of kiloparsecs. How does that connection work? That's fueled a lot of research careers too, including mine lately. Right, so understanding how that works. And there are people who do magnificent simulations. This is a movie of the illustrious simulation, not TNG, but the original illustrious simulation. Their movies are particularly cinematic. This one's rotating, so you can see the 3D structure. You've probably seen movies like this before. In the first part of it, it's showing gravity assembling dark matter into halos. Once we get to 3 billion years simulation time, the color map will change, so you can see gas temperature, where the red parts will be the hot parts and the blue parts will be the cold parts. Once that happens, you will also be able to witness feedback in action, or at least feedback as it's manifested in this computation. So here it is. You can see energetic things happening because it's flashing, right? And then you get outbursts. And when you see these things that look like explosions, that's the black hole feedback algorithm erupting, putting a lot of energy in the surroundings, and spreading gas far and wide. When we move to the next color map, you'll see the enrichment. So the enriched parts will be green. The purple parts will be not as rich. And you'll see that not only are black holes, or is black hole feedback heating gas and pushing it out, but it's also tending to spread the products of chemical evolution of galaxies across large scales. And I think we are going to make the switch to enrichment here. Okay, see now you have purple and green. The green parts are more enriched where the galaxies are, but there's a lot of purple out there. And it's gotten out there partly, this is some because of supernova-driven outflows, but also significantly through black hole-driven outflows. So this again, I've described this figure before, and this is fairly recent paper from the TNG group. And given that the baryons are pushed out, and really, I think as a field, a lot of people have treated outflows by saying, well, there's an outflow, and once the baryons go beyond the Vera radius, we say goodbye. There might as well be at infinity, and we'll forget about them. I think that's a mistake, because the gravitational potential energy that all this stuff has gained is the fossil record of all the feedback that's happened in the history of the universe. Right? It's like the region around a massive halo is a giant bolometer for feedback, and understanding the distribution of this stuff is really diagnostic as to what's happened over all cosmic time. On this side, this is from the same paper, and what's plotted here is halo mass on this axis. On this axis is something the authors call closure radius. It's asking the question, if I look at a halo, the halo should have, the halo initially begins, the matter associated with the halo with this cosmic mean baryon fraction. After all this has happened, how big a radius do I need to draw around that halo to encompass the baryon mean, the universal mean? In TNG, that curve looks something like this. So and around a Milky Way type galaxy, you have to look out to about 3 times the canonical virial radius to find all the baryons. And then if you go up to galaxy clusters, you finally get to, well, we can see all the baryons up here. The most important thing to notice about this is the vast difference between these flagship numerical simulations. This means we have no idea how to model it. So A, we're not getting things modeled consistently from simulation to simulation. And B, the real constraint is how these baryons distributed in large, around large areas. And there's going to be a lot of progress on that in the next decade through Sunyaev-Zadovich effect observations, through fast radio burst observations, which probe the electron density along lines of sight. Even gravitational lensing, when you get down to size scales of several hundred parsecs, you move baryons around, that's 16% of the mass, and now that's going to matter to gravitational lensing and gravitational lensing cosmology. They're aware of this. So one byproduct of high precision, large scale gravitational lensing is going to be an idea of how baryons, constraints on how baryons have been redistributed. And that feeds back, literally, I didn't mean that pun, that feeds back into what has the black hole been doing in big halo over cosmic time? So ask, well, what constraints are there at the moment? This is what comes from mostly from X-ray observations. So if you try to count up all the baryons associated with the galaxy cluster, you find you get close to the cosmic mean. Okay. So whatever's gone on a cluster hasn't lifted baryons significantly out of that halo. But when you go down to halo masses of 10 to the 14 or 10 to the 13, there's a significant deficit. So either you somehow vanish them from sight, or you've lifted half the baryons out beyond, in this case, the radius people call R500, which is not quite as far as what most people think the virial radius, but it's about as far as you can observe with an X-ray telescope when you're looking at things in this scale. The thing is, when you ask how much energy, so you can ask how much energy does it take to push gas, that much gas out, you can get an estimate by saying, well, I know what the energy per particle is from the gas temperature. If I know the halo mass, I can say how many baryons were originally associated with that amount of matter. You get an estimate for the circumgalactic binding energy. For a group, that's 10 to the 60 to 61 ergs. And over cosmic time, that's a time average power of 10 to the 43, 10 to the 44 ergs per second. That's what it takes to actually lift stuff out of a halo like that. And that's generally quite a bit greater than the current X-ray luminosity. So really, whatever has done this has really put in a lot more energy than it just takes to replace radiative cooling. You had to do that and push it out. And it really takes an order of magnitude more energy to get that density suppressed. Okay, so this now is one of the key figures of a review article that Megan and I did last year. It's 110 pages, but really gripping reading. Okay. And the diagram's kind of complicated, so I'll go through step by step. Okay, so on the bottom axis, there's an atmospheric temperature scale, okay, which you can measure with an X-ray telescope. On the top axis, there's a well understood X-ray temperature halo mass relation. And so if you can measure an X-ray temperature, you can infer halo mass from that. Okay. If you have a temperature and a halo mass, you can calculate what the CGM binding energy scale is and relate it to this axis over here. So I'll stop there for a second and say, if you have a halo mass, you also know the typical stellar mass of a galaxy that lives in a halo of that mass. And you can say how much supernova energy could come out of the galaxy over cosmic time with one of those stars. And that's this red line. Okay. Now, maybe you can't transfer all that supernova energy to the circle reckoning. Maybe you can only transfer 10%. And that's this red line. So this is the 10% to 100% efficiency supernova energy transfer you can have in circumgalactic medium. And this is the binding energy. So below the Milky Way M31 scale, the energy that comes out of supernova is sufficient to move around the gas all the way around the galaxy. But if you keep going up, this bends over because the stellar mass to halo mass relation starts going the other way. And you can even argue, well, what if we use all supernovae and all the stars that are in the halo, and that's this line, but you get up to 10 to 13.5, and even that's not enough. Okay. So that's the story from supernovae. If you think you see black holes plotted in this diagram, you can tell what the black holes are supposed to be from the point style. So these are black holes. And so this is black hole mass versus the temperature of the circumgalactic gas around the galaxy. And I haven't told you something about the vertical scale yet, but what you can see is the temperature black hole mass relation is saying that the black hole mass seems to be linearly proportional to the binding energy of the circumgalactic gas all the way up to 10 to the 14 solar masses. Okay. To make that line up, you have to choose a normalization factor. Okay. And that normalization factor is down here. So from the observed black hole masses and the observed X-ray temperatures, what you infer is to budge the baryons in that massive halo, you need to put in about 0.5% of the black hole rest mass energy. And so that's an important integral constraint on what feedback does. Another thing that's on here is the X-ray luminosity of a given halo multiplied by 1 over h naught. That's like if they had the same X-ray luminosity over all of cosmic time, how much energy would come out. And in the previous decade, I was paying a lot of attention to galaxy clusters. Where in galaxy clusters, it looks like feedback from the black hole is putting about the same amount of energy as is lost to radiation. And we were thinking that that's how feedback seems to work on galaxy cluster scales. But what's happening here is something different. The black hole is putting in at least an order of magnitude more energy than you need to compensate for radiative losses. So there's a different kind of feedback relationship there. So I presented this research. Well, okay, I should put this up. Yeah, so those are the takeaways. Right. If you want supernovae to be controlling the behavior of the atmosphere around a galaxy, it takes about 25% of the supernova energy to do that. You know, below the Milky Way scale. Above it, you fall short, and to start pushing around the gas in a more massive halo, you need to put in about 0.5% of the black hole rest mass energy.
And just to kind of, I know very little about that.
Yes.
25% supernova energy. Is that a reasonable number based upon?
Okay, that's actually a very good question, because it's been debated for decades and it's launched a zillion numerical simulations. And the problem is when you try to model supernova in a simulation, they tend to be going off in complex gaseous environments. And it's all too easy in your simulation to end up putting energy into a cloud that radiates like crazy. And so actually getting supernova to be effective has pushed people to do all kinds of numerical tricks and approaches to tap the supernova energy more efficiently. The most recent high resolution simulations suggest that 20% is a reasonable number, but 100% probably isn't.
Sorry, maybe this is tangent, but is this a reasonable number? And is that calculated through detailed physical considerations, or more a case of by higher number of 20%, we should with a higher number of 100% instead?
You clearly spent a few years around science. Right. I think, yeah, so people have been worrying about this since the 90s. And I think in the early days, it's like, how can we soup up our simulation, do anything at all? Yeah. Right. So it's like, you're in that world. Yeah. There's a group led by Phil Hopkins, Caltech, the fire people and fire sensor feedback and realistic environment. So they tried to go to super high resolution model, stellar wind interactions and radiation and like everything you can figure with high resolution. And what they argue is when you stick to calibratable algorithms and you put them all together, it does pretty well. There are also people, one of my close collaborators, Greg Bryan at the Flatiron Institute in Columbia, and he has a number of collaborators who have been doing even smaller scale simulations, trying to say, if I simulate supernovae in a complex disk environment, high resolution, like Eve Osterker has also done this, what kind of venting efficiency should I get? People have talked about something called Voit. In the wind field, people have talked for years about mass loading factor. What they mean is if you have a certain stellar mass, stellar formation rate, what do I have to multiply that by to get the wind mass flow rate? Now people are talking more about energy loading, by which they mean this efficiency. And so in Greg's experiments, what he's finding is when you're producing a wind in a lower mass galaxy, most of the mass tends to come out in cold clouds, and much of the energy comes out in the hot intercloud medium. So the mass loading factor is like attached to one thing, and the energy is attached to another thing. But getting that number there's a large literature on it, and it's not easy. And I would say, yeah, the circumstantial evidence is that this has the same slope as this, right? In fact, and people notice this. This goes back to, I think, Larson, like 1974, and then Deckel and Silk and all that. Like, it's plausible the supernova limiting the growth. Showing that you can actually tap that much energy is super complicated. All right. So, yeah. All right. So I was pretty happy with that figure. And I went on the conference circuit last night. And the simulator said, well, we don't see that at all. At least that black hole mass relation. So, so I decided I had to dig a little more into the black hole mass halo mass relation. And there's this famous paper in 2002 showing so Laura combined estimates of halo mass from stellar velocity dispersion and circular velocity in spiral galaxies to try to understand what the black hole mass to halo mass relation was, and found just what you'd expect if you think that black holes are actually pushing gas out of the halo. Makes perfect sense, right? Well, not to everybody. I won't go into the details. You could probably ask Laura sometime how much of a hard time people gave her for this.
I forgot.
I'm sorry. Okay, I'll give you a spoiler. I'm going to show stuff that totally vindicates you. Totally, right? Yeah. I mean, I think a certain senior star, didn't they publish a Nature paper saying, I'll paraphrase, the black hole mass is not related to the halo mass at all. Right. Yeah. So anyway, okay. So this is Laura's work, and the kind of the golden thing here is really the black hole mass is a superlinear function of halo mass. So there are a lot of people who believe that black holes grow in high mass halos mostly because you're just assembling them through mergers. In which case you wouldn't expect this relation to be any steeper than linear. If it's steeper than linear, the black hole mass is actually responding to the halo as a whole, and not just we're just putting together pre-existing pieces. Okay. Well, here's another piece of work that was done here. Well, Laura wasn't here when she did the work, but there's this piece of work by Bandara, the right way to pronounce it, Bandara, Crampton, and Smarad, where this is not quite a black hole mass halo mass relation, because to do this sample, they had to infer black hole masses from sigma v using that relation, but you could get actual halo masses from lensing, and the points were consistent with this relation. There might be, Laura tried a few different methods for estimating what the normalization should be, and I think the slope was more important from that paper than the normalization. You can see these things are parallel to each other. They're showing this superlinear slope. A year later, there was a really elegant simulation experiment done by Booth and Shea, where they put a fairly simple black hole feedback algorithm into the simulations that eventually become the Eagle simulations. And they said, we don't know what the efficiency factor should be, but we're just going to tune it. And as they turned the efficiency factor up and down for black hole energy transfer, they found very robustly, they got the same scaling law, okay, consistent with, or close to consistent with this proportionality. And so it was because once the black hole put out enough energy to budge the gas around it, the feeding would go down, okay? So again, this seems to make perfect sense. The most recent compilation I know about is Marasco et al., where there's their points. This line is for Ray City, 2002. But it's a little hard to understand all the biases that might be inherent in this particular treatment, because these are a number of different halo mass tracers. It's a very heterogeneous set of halo mass tracers. In a way, once you have a set of what you think are well-measured black hole masses, the trick becomes, well, what should we be using for halo mass? How good is that halo mass tracer? What biases could there be? So, so these are the relations that I've showed you so far, which all are really close to parallel to each other and consistent with this kind of very, I would say, simple and conceptually appealing picture for how black holes are responding to their environment, okay? And this is the one-to-one relation. And now we get to, where I entered into this, dive into the literature is the black points that I showed you a few slides ago are for a compilation, from a compilation by Max Gasperi and collaborators in 2019, where he was looking at a sample of galaxies that all had X-ray data sufficient to measure temperatures. Okay, so that's kind of how it's the selection bias is these galaxies all have good X-ray data and have dynamically measured black hole masses. And so the usefulness of that is X-ray temperature is one of our best ways of getting at what a halo masses actually are. So there they are. So now I'm going to have to, there's a way in which I've carefully chosen which temperature measurement to use. In this paper, they compare black hole masses to many different galaxy and X-ray observables. And the most highly correlated thing with black hole mass in their sample is the temperature of the gas within a few effective radii of the galaxy. It's even more correlated with that than with the stellar velocity dispersion. Okay. The picture looks a little bit different if you ask, what about the temperature of the whole halo? Okay. These are the same galaxies. In fact, this is NGC 4889 in the Coma cluster, where if you look close to that galaxy, you get a temperature about 2.4 keV. And if you look at the halo as a whole, you get more like 7 or 8, because it actually is a 10 to the 15 solar mass halo. And in the reason that Megan and I, in doing our review article, chose these points rather than those points is the black points are the tightest relation, and we wanted to know why. We wanted to come up with an explanation for why that is. And the suggestion I'm going to put on the table for you is, if you ask about the history of this galaxy, there's a time when it was forming stars, and its black hole kicked in and pushed the gas out. That might have been a long time ago. And so we think this temperature of responding to the potential near the galaxy is more indicative of what the potential of that galaxy was like when that event happened and the black hole grew. If in the intervening 10 billion years, it found itself at the center of a cluster but didn't grow that much, then your point is over here. So you can see there's a gradual trend of points shifting farther over here as you get above kind of the 14 solar masses. So what we think is this very tight relation is baked in, at the time the black hole's actually pushing gas out. But in some cases, you end up in the center of a cluster of galaxies where you didn't push the gas out because you can't. And so if you include those points, you get a flatter relation that's not quite as indicative of the scaling that comes out at lower masses. Okay. That's the illustrious TNG simulation. That's why they told me, we don't see anything like what you're claiming. Okay. And so the reason I went through that whole literature history is I was trying to figure out, like, well, what should it be like? So that's illustrious TNG. You can also put the Eagle simulation on here, and Eagle is a little bit better in this range, but then it seems to undershoot the actual black hole masses once you get to more massive halos. Okay, so current state-of-the-art cosmological simulations are not yet reproducing this relationship, which seems so intuitively appealing. So then the next thing I had to figure out is what's going on in illustrious TNG in particular. I did want to show you a few more things. Do you also ask about other mass proxies? X-ray observations can't tell you much about things with temperatures less than 0.2 keV. But you can use sigma V as a proxy for those. And in fact, there's quite a tight sigma V temperature relation. So you can consider almost the sigma V and CGM temperature relation is all of a piece. But if you only use sigma V, what you find is there's an issue when you get up to 300 kilometers per second. When you go up in halo mass, the galaxy's central velocity dispersion gets bigger and bigger until you start getting cluster scales, and that just saturates. And the black hole mass sigma V relation just kind of starts going to a much higher power law here. And that seems to be because black hole feedback keeps galaxies' stellar velocity dispersion from growing much past 300 kilometers per second. But that's another talk. I gave that one yesterday. So that's the story if you just use sigma V as a proxy. But it seems clear that if you then say, what about CGM temperature? It's extending along the same basic power law because it's more sensitive to the larger environment than sigma V is. There's also using stellar mass, and so these points that are colored here, they're from the papers by Brian Terrazas and Eric Bell. And they have shaped my thinking a lot because they asked if we look at galaxies as similar stellar mass. So these points are related to this stellar mass axis now. The stellar mass axis is related to halo mass through abundance matching relations. That's how the top axis is related to the bottom one. And for a given stellar mass, there's a very wide dispersion in black hole mass. And the color scale of the points, the filled blue ones are the fastest star formers, then the anti-blue ones, then the red triangles, and then the filled red triangles. That's a sequence of declining specific star formation rate. And there's a very clear anti-correlation between black hole mass and specific star formation rate at fixed stellar mass. And that seems to indicate that black hole mass growth is shutting off star formation. This is consistent with the picture. But it also says, beware of using stellar mass as a proxy or for black hole mass. Yeah.
Check the next. There's also going to be galaxies that, for whatever reason, have a star formation preferentially low.
In a way, I can't rule that out. Maybe that's what happened. Yeah. So I'm in the scientist trap called. There's an explanation I find so appealing that when I see data like this, I say, but of course, right? So but I think this is very interesting terrain at the moment. There's clearly it given stellar mass. Well, the way I would think about it is, without passing judgment on the chicken or the egg, it looks like probably at a given halo mass, the black hole mass and stellar mass are anti-correlated. That's the interpretation neutral way of making that statement. Why that's the case? Well, that's an interesting problem. Okay. All right. So if things are looking like this, why is this particular simulation getting such a discrepant set of black hole masses? So you can look at the star formation quenching behavior. And this is a plot of illustrative TNG where you have halo mass on this axis. And this is the cumulative injected kinetic energy from the black hole. This line is the binding energy of the halo's variant. And the transition to a low star formation rate occurs almost immediately after the black hole's injected enough energy to lift the gas around the galaxy. And that's the case at Z of 0. Okay, I'll get to this. So you might ask, how much black hole growth is necessary to bring about this transition? And what I'm going to point to is, in their simulation algorithm, they used an efficiency factor of 20%. As I talked about earlier, only 0.5% is actually necessary. So really, to do this, they don't need a whole lot of more black hole mass growth to get all this to happen, because they just chose this number. Okay. But the next few slides are showing you go to Z of 0.5, you go to Z of 1, you go to Z of 2, you go to Z of 3. And the relationship between highly quenched star formation and the black hole put in enough kinetic energy to lift the gas around it is very distinct. Okay. So that conforms to this idea that black holes are shutting off star formation by pushing the gas out of the halo at large. Now there's another detail of illustrative TNG to pay attention to. This is because, okay, there are gaps here because lunch ran too long. I didn't finish all the slides. Beware of presenting something for the first time. What this graph shows is black hole mass here, and cumulative energy injected in the form of kinetic energy. So in the simulation, the black hole feedback has two modes. One is a thermal mode. When the accretion rate is close to Eddington, the feedback algorithm is injecting energy in a thermal mode. And when it drops enough below Eddington, it switches to a kinetic mode. Okay. And what I showed you in the previous set of slides is the kinetic mode seems to be the one that makes the difference, because the thermal mode suffers from this problem we talked about, the supernova. In their simulations, the thermal mode dumps in a lot of energy that gets radiated. Okay. And so it's not until the black hole switches to the kinetic mode that we really start pushing the gas around. Okay. And in their feedback algorithm, it's set up so that happens at a black hole mass of about 10 to the 8. So as the black hole's mass approaches and surpasses 10 to the 8, the finger on the scale deciding whether you're in kinetic mode or feedback mode tips to kinetic mode. And so the green is indicating black holes that are primarily in thermal mode, but because some cumulative energy has come out in kinetic mode, right? It's in kinetic mode some of the time. But once it's put in enough energy through kinetic mode, you start lifting all the gas, it finds itself in kinetic mode almost full time. Okay. So that's what this graph is trying to represent. And so part of what's going on is you have to have a high enough mass black hole so the algorithm says, okay, it's okay to do kinetic mode. But you don't switch to full-time kinetic mode until you put enough energy. So this is almost part and parcel of the switch to quenching, because you're trying to lower the gas that's in the galaxy. And this phenomenon stays true as you go to higher and higher redshifts, you can see that the transition mass is like marching over this way a little bit, but the actual transition keeps happening right at this line. Right. Okay, the last TNG little set here is illustrating lifting. And you probably can guess what goes on when you ask, in which kind of systems is the halo gas fraction suppressed? And so the red is indicating you've done very significant lifting of the atmosphere. And the orange and yellow are not so much. And, down here, you kind of have most of the gas that should be in halos in the halo. And when you put enough black hole energy to lift it, it gets lifted up until you get up to galaxy cluster scales. And then it no longer puts in enough energy to lift it. Okay. And so, so this is again, true as a function of redshift. So there's this very tight connection in the simulation between lifting, quenching, and total kinetic feedback. So why this ends up so discrepant is the algorithm builds a 10 to the 8 solar mass black hole at a halo mass of about 10 to 12 and quenches galaxies when they get about 10 to 12. That recreates galaxy evolution phenomenology very well. But now you have a 10 to the 8 solar mass black hole and 10 to 12 solar mass galaxy. On the data say it should actually only be 10 to 7. Okay. Then, as you merge things, you have a whole lot of black hole mass that you made long ago, and you're assembling it in black hole mergers. Meanwhile, these things are putting out. This is the way. In this stage, they can lift the gas around them with hardly any additional black hole mass growth. So, in a way, what's happening unless there's TNG has all the elements necessary to reproduce the black hole mass goes like halo mass to the 5/3 law, except the algorithm conceals all that. What you get instead is, well, we had to get a lot of black hole mass before anything of use happened to stop star formation. And then once you have that much black hole mass, the additional black hole mass you need to quench and lift does not really show up compared to what's already there. And so, yeah, I guess, so I'm trying to figure out how to tell them more. I'm not sure the story has a moral. Except that sometimes when people say, well, we don't see that at all in simulations, you need to look a little deeper as to, well, why didn't you see that in simulations? But rather than ending on a pessimistic note, I wanted to go back to this. Because, yeah, I made this view graph just yesterday, and I found it particularly beautiful, probably because I left off all the complicating factors. But the hypothesis that this relationship should show up goes back to a paper by Silk and Reese in 1990, where I'm not sure they have the whole halo in mind. They're just saying, maybe the black hole could look at gas out of a galaxy, it had to unbind gas somehow. And there's been a whole lot of other stuff talked about that governs black hole growth. You can try to make it stellar bulge mass or mergers or many, many different things. This figure seems to have a lot of purity to it. In particular, the halo masses here are pretty legitimately measured halo masses. And they show there's a connection that seems to run from 10 to the 12 solar masses to at least 10 to the 14. And it's exactly what you might guess from the kind of, I guess, most conceptual, basic idea about what the black hole is doing to the environment around it. So here's my conclusions. I underlined and bolded and indicated. Okay. But I'll just take your questions now. Yeah, want me to switch the owl?
Yeah, the owl is selected.
And there's two of them that you need to do, sorry.
Oh.
It's a speaker and a microphone. It's the same button. But a different thing.
Yeah, things like, I don't. The
I think
message
we
is
just
just,
click on green there.
pardon? Okay, there you go. All right, so,
Oh, they're both on out.
They're both-
Sorry, thanks.
Great.
oh, I forgot, and now we're word from our sponsors. Great. So, Deborah is going to be the very first of you to earn a lovely mug for contributing to the forum on Black Arrows. It's Department of Magic Publishing, where yeah, some of us have found it's hard to keep up with archive. Yeah, Jay, nothing with it. So what if we could post little kind of media-rich introductions to the research we're doing that might be a 5-minute video, well, actually less than 5-minute video, or a particularly interesting figure, say a little about it, and point people to the real article if they're more interested. So for a limited time only, contributors get wonderful promotional mugs. Yeah. And the thrill of seeing their own work highlighted on the Black Atmospheres Forum. I only have 2 cards left that I leave with Deborah, because she already has one, to distribute to whoever wants to, or is interested in even looking at the forum, to see what this is all about. And so that's, I can't go back. I'll put on the conclusions. And yeah, so thank you for listening to our sponsorship. Questions?
Okay, great. We do already have a question online from Kevin. He says, is there any simulation work at smaller scales which better models the black hole feedback efficiency from more first principles?
That's a very interesting question. So I think there are 2 efficiencies. Well, 2 basic categories of efficiency that matter. One is when gas accretes on a black hole, how much of the rest mass energy is coming out in the outflow. And people who actually try to model that using like GRMHD and stuff, they get numbers that are actually higher than what's needed. Okay, I don't yet know what to make of that. The other thing is, as this fire hose is passing through, how much is retained? And so that's a little harder to model from first principles, because how much of that outflow energy is retained depends on things like how collimated is it. What kind of viscosity does it affects it as it plows through the inner black medium, right? And so I think the problem separates into the problem at small scales. You know, when you're feeding a black hole, what's the actual mechanism that produces gas coming out, right? And then what's the coupling of that? So there's like the parsec scale problem and the 100 kiloparsec scale problem, and you can't do them all in one simulation. It's going to be impossible for decades. And there are like these estimates of like how many power plants would you need to build a computer that could do that simulation? It's kind of funny when you do kind of sad. But for the time being, we can't do them both in the same simulation. But so it separates. But yeah, for people, we're trying to do a better job of it. And I think what I showed early is current simulations, the black hole is a very blunt instrument that we don't really understand. But I think the good thing is the data seem indicating there is a rather intimate tuning that happens, and we have to figure it out.
So if one of the subtle points I'm taking from your talk is that the illustrious guys chose the wrong value of energy out.
Yeah.
but I get a lot of other things really right.
Yes.
In my eyes, so then to me, that kind of implies that they must also be getting something else wrong that's balancing that. Do
Right.
you have any thoughts as to what that
Okay.
might be?
So, sometimes it's funny how, yeah, it's funny to me at least, how research can go. Because, I went to this conference in August, I came on, I had to figure out about one. And so I had a senior thesis student who we set up with a project where we wanted to do is just take illustrious merger trees. Say, here's how the black hole is growing through mergers and fueling. And change what happens at the nodes, like, can we do a different weighting? And that project is sort of going slower than I wanted it to. But you can do this, right? You can do this kind of thing. But then, when I wrote a draft, showing how what's happening under the hood of velocity is quite consistent with this lifting and quenching picture. And they said, we pretty much agree with what you say there, but we're not yet convinced that the observations are inconsistent with illustrative G. So then I went back and started marching to the literature, like, no, I think they are. And so the paper kind of grew another wing, which was most of that long build about the relation. And so what it comes down to is two numbers. Well, okay. Well, two numbers in a choice. So there's a pivot math where you put it into the system to help govern the switchover math at which the black hole switches the kinetic feedback. So there's that number. And then there's the efficiency factor when you're in the kinetic regime. So in order to get things to work out, you need to have a lower pivot mass. So that you don't have to go all the way to the 8 for kinetic feedback. And you need to have a lower efficiency when you're in kinetic mode, right? And so that's the thing you can test with merger trees. The thing, but they did make the choices they did because they're trying to get the stellar luminosity functions right. Okay. So if you reduce the pivot mass, it's possible that quenching could happen too early, and then things would be wrong. So it's a kind of a tricky game. And I think another choice that's not a parameter choice, but it's the choice saying when we're in thermal mode, there's no kinetic output at all. Okay. It's a binary choice. And yet, there are quasars that seem to be creating near the Eddington limit that also have big jets. Okay. Is it correct to say when the Eddington rate is high, there's nothing coming out? It's more defensible from a modeling standpoint to kind of make that binary switch, but it might be part of the problem. It's insufficiently realistic. So to the extent you care about getting the black hole mass halo mass relation right, they have to re-engineer something. Okay. But what they shouldn't be doing is telling people, well, we don't see that in the simulation, your interpretation must be incorrect. That's a step too. Yeah.
So based on what you just said, then is it different choices for the pivot mass and the efficiency that led the Eagle simulations to be more nearly
Okay.
correct?
The Eagle simulation takes a completely different approach to feedback. So given that dumping thermal energy in, you risk radiating too much of it away. What the Eagle people have done for a long time is they, in a way, they save up the energy until they can release it in gas that's all high temperature that suppresses cooling. They pick a temperature and say, we're going to save up the energy until we can release a blob of gas that's 10 to the 8th degree. Okay. And then their feedback becomes successful because radiative losses are not catastrophic. They know it's artificial, but it brings about some results that are in reasonable agreement. Okay. But what seems to be happening is when you get up to past 10 to the 13 in halo mass, that's not well enough tuned, right? Or what should I say? Should be careful using the word tuning. The data indicate that there's still an intimate connection between black hole mass and the gas at kiloparsecs, tens of kiloparsecs distances that the Eagle simulation is no longer responding to. Right? The Eagle black hole masses are no longer climbing. From 10 to 12 to 10 to 13, they're climbing on a pretty steep slope, and then it flattens off. Okay, and so whatever led to success early on is broken down at higher halo mass. It's hard to pin, what exactly does it take? But if I were giving my other talk, who wants to go for another hour? My suspicion is that it has to do with the jet. Well, it's a few things. One of it is the jet-like nature of feedback. That morphologically, energy seems to drill a long way before getting done. And that's not what happens in these simulations. Okay, that's kind of thing one. Thing two, if I'm giving another talk, I'd be pointing out that as you climb in stellar velocity dispersion, what you're creating is a potential that's very hard to push gas out of. And all the gradients get steeper, the pressure gradient, the density gradient. And you flip over to a state then where all the cooling happens at the center. And the rate of the cooling depends on what the confining pressure is at large radii. And I argue in other papers elsewhere that that's what's actually limiting galaxy velocity dispersion. Once it gets too high, cooling gets focused on the center, and the cooling rate is determined by pressure that's confining the gas throughout the galaxy. And the black hole has to now lift the gas in order to relieve the cooling rate on it. And so this is kind of a mental shift that's taken me a few years to make, because we were so focused on feedback, heat balancing cooling, the singular fiber clusters, but it's not what's happening on group scales. What appears to be happening is the black hole is down at the bottom of a huge pile of gas and getting fed like crazy until it can relieve the pressure at large distances. And that's a different feedback mechanism heat equals to. Yeah, I can like draw diagrams and say it in words, but we're trying to realize it in simulations and it takes more time. And it may be a while before it's actually done in cosmological simulations, because it might take a lot of resolution.
All right, so we've reached the hour, so let's
Okay.
thank Mark again. And Mark is a couple meetings